what the frick are we doing here right now? So we want to build a real space application. So we want to have telemetry and tracking, and with a real purpose. For my University of Stuttgart, there's a small satellite project at the IRS. That's the Institute of Space Systems. And they want to build a small satellite, and we want to track and do telemetry with it when it's done in orbit. And we want to determine the orbital elements, that's called Keplerian elements, that define the orbit. And we want to have the amateur radio community included in this all. And we want to have it externally tracking and positioning, because it has some benefits with it. So why do we want to do it? So why not? So first of all, it's positioning. When the satellite is ejected into the orbit, sometimes you don't really know where the launcher is heading you to. So you're bored in orbit, and sometimes you're not there. And you want to know where the launcher put you to. So relatively fast after the positioning of orbit injection, you want to have the positioning. So like you can see here before on the slide. When there are so small variants inside, you are not aiming with your dish directly to the satellites, and so you don't get any connections at all. And we want to have it globally, and we want to have an independent service. Then afterwards, when the tracking is possible, we want to have also some kind of communication with the satellites. In this case, it's a so-called data dump mode. We want to get signals from the satellite, like some housekeeping data, the temperatures inside, and some other really important data that will be sent down. Then our distributed ground station network over there could fill in some gaps between the main nodes the satellite owner already rented, so you can fill some gaps over there. And the very, very last end of it, we want to have a possibility to command satellites. Okay, that's a really, really high expectation here. And there's almost nothing more important than data rates in space, so you could help us doing this and achieving it to be somehow a little bit cheaper then. And the last thing is, of course, to serve man in general, to have the telemetry and tracking of satellites for everybody, some derivatives beyond this current objectives, of course, and a science platform. And that's a picture how it's done currently. So there's big satellite dish on some fields. That's a Rasting Satellite Earth Station, and we want to have something like this. That's that's somewhere nearby in Berlin or Köln, and everybody should contribute, like not perhaps with this television satellite dishes, but with some other kind of antennas these guys are building right now. So how do we start? First of all, we need 4 dots, and these dots are reception stations. And we want to have some kind of reverse GPS, so you need to have at least 4 GPS satellites and a handheld device. And with 4 GPS satellites sending signals to your handheld device can calculate where it is. So we want to have it backwards. Your handheld device will send out something to the antenna, to the reception station, and then we will calculate it backwards. And this is done via pseudo-ranging, it's so called, and we have to have at least 4 stations because it's in 3D. And this is, it's easy somehow, but it's solving lots of linear equations with matrices. So that is nothing new. So the so-called Apollonius of Perga did this some 1,000 years ago, and his finding is already available in the internet. And there are some other papers describing how it will be done. So it won't end with 4 dots. We need to have U at some point, because we want to have more reception stations distributed all over the world. Because then we can enhance the accuracy of everything through multi-reception points, and then it will become a combinatorial problem with some exponential deterministic behavior. So the more stations you got, the more the computer has to calculate afterwards, but like shown here, your position accuracy will be much, much better, or at least we hope so. And now it's my turn. I'm from the Constellation platform that's already existing right now. We want to turn this basis and do this into a sensor grid. And we are a student group We are a DGLR, that's the German Aerospace Society group, a young academics group, and we do applied sciences and use-oriented aerospace research right now. And it's a really interdisciplinary collaboration. Like I said before, DGLR, Rechenkraft.net, SafeNet, some of them are already here, and of course CheckSpace. So it's really, really interesting. And what we're basically doing is this, but that's not our machine. That's the HLRS. That's a supercomputer also based in Stuttgart. They are on the 12th place in the top 500 ranking. They have about 800 teraflops, but they cost 30 millions. And we are this small. Because we are relying on your computers, I will tell you afterwards. We have 2 teraflops right now. That's so in this range, but we only cost 300 euros. So it's rather cheap in this position. So and how do we do it? We do distributed computing with Boink. I think everybody knows this. So you guys are donating idle PC time to science, in this case to our system. And we have about 2,000 users and 5,000 hosts PCs. And if we only can make 10% of them plugging in the antenna these guys are building, then we have a huge basis already distributed in about 66 countries all over the world. And currently they have nothing to do, just spending some idle time for a so-called ascent trajectory optimizer for a high-end student group at our university, and I'm doing the thrust optimization of them for the hybrid rocket system. So we could possibly and hopefully turn some of them and plugging in the antennas, so we also already get some distributed computing system as a basis of this. And we want to have the sensor data processed also on our system. And we also want to make these data available in raw form. So you can already start doing some good things for science currently right now. So this is nothing new. This has already been done. The Quakecatcher network is already doing this with some accelerometers built in some Macs, or with a small USB device you can plug in anywhere. And that's my favorite. It's called Radioactive at Home. You can measure radioactive background stuff at your home. So that's nothing new. You have this as another application. So going back to you, and we need some more help with volunteers. That are you, amateur radio experts, and of course institutes like universities and other important persons. And we want to have antenna modes with fixed single antennas. That's the basic stuff everybody can participate in. Fixed triple directional antennas. That will be more costly because there are 3 of them, but they give us more possibilities afterwards. And of course motorized single directional antennas with high gain antennas like satellite dishes. That will be done by the institutes because they're really big and expensive. And with this kind of hybrid antenna mode, we expect that the accuracy will be much better afterwards. And the expected sensor grid we want to have is at least 1,000, but over 9,000 would be very, very appreciated. Okay. We are also thinking about doing some more mathematics. So there's this so-called one-way ranging, sending something from Earth to the satellites and back. But we are not in the sending mode right now, but we are already thinking about it. It's a so-called one-way Doppler system from the French guys using this for Doris. Multi-way ranging, that is what we expect with a distributed sensor system as well. And we have some contact with Dr. Sakamoto from Tohoku University in Japan, who does some crazy stuff and good things with Doppler shift experiments. I'm not really knowing anything about because I don't understand it, but it's working because he's doing it right now. And when you have some ideas how we could do this, give me an email, please. So why do we do it? For science, of course. And for other reasons, like I presented before. Okay. Now to give you some impression where we are placed, because you can say, perhaps there is a system currently doing this. Yes, of course. You can do it with inertial measurement systems. And I think some of you already do, and with UAVs and so on. And of course, a space-based satellite navigation system like GPS or GLONASS. The GPS is operated by the US Department of Defense, and GLONASS is now controlled by the Roscosmos, the space agency of Russia. And they have something in common. When your satellite gets lost, because everything is stored on the satellite, you don't get any data back. So it's nothing worse when you know where you are, when you're not sending it to the satellite owner afterwards. So we want to have it externally, and the governmental agencies already doing this with NOAA and United States Strategic Command. They're tracking everything with radars that's greater than 2 centimeters, like a coin. The European Space Tracking S-Track, and the so-called goals of the CNES, like I mentioned before. So they have different objectives, different functions, and they are under different management. And the distributed ground station network could become a new player in between them with the decentralized responsibilities. So what else can we do afterwards when we really achieving our goals? There are some crazy papers on the internet I really love, like atmospheric measurements or just measuring the accuracy of the GPS itself, because that's also important, because you want to know when something is going blurry on your radar. Then environmental monitoring by wireless communication networks, that they proved that you can already do measurements in the atmosphere with UMTS and GPS, so it's basically the same. We have to just figure out how the frequency is playing in this. Perhaps thunderstorm, strikes and cell detection, or that's my favorite, nuclear detonation detection. I'm not sure how it works, but I found a paper explaining this, and I would really love to detect one. So not because the detection, but I want to prove somebody is playing around in their foregarden. Okay. We talked about the antenna system. We also need a beacon. That's a concept, nothing more. We want to transmit something. We need a protocol for it. We have to establish a data rate, what we need for the complete cycle, and of course for the use data, that's important. And the ham radio community know OSCAR, that's the orbital satellite carrying amateur radio. I would also like to have an own ID for our purposes. And in this case, there's another interdisciplinary partner, the Aerospace Lab in Stuttgart-Herrenberg. They are high school students, and we want to have them build and helping us with the beacon itself. And the beacon itself should be as simple as possible to have more possibilities with it, because I will come to this later. And now you could ask us, okay, do you really think you can do this? Yes, of course. There's a Fun Cube, that's a small satellite lying on the floor there. It's built in the United Kingdom, and they have something called the Fun Cube dongle. It's such small, and they already can receive signals from space, so with some data rates in it. So it's very, very possible to do this. And now for the future perspective, besides the time measuring, the first thing I would love to have is tracking satellites, of course, tracking aircrafts, that's currently being done. Then helping science experiments or weather balloon, that's a Rexus and Bexus campaign, that's a rocket and balloon experiment for university students. You can apply for it for a small slot and put your experiment on board both, and perhaps that's a really nice test bed for us later on, for our beacon and also tracking them. UAVs, these guys, the UAV NG is currently doing some great job, some stairs up. And of course, for the Stuttgart Adler, that's also a plane, a small plane, and we also would like to help them as well. Of course, OpenStreetMap, because when you have a beacon that's really, really small and fitting into your pocket, you can do your walk around and then checking where you have been, and then helping OpenStreetMap doing the material, the mapping stuff, and like mentioned before, the differential GPS, improving your GPS system, and of course, animal tracking. Future perspective and chances beyond the system. So our platform constellation could be the first application for the distributed ground station network, but it's not exclusively done for us, because spin-offs and derivatives should be done for everybody. And like I said before, I would love to have some small devices, and in this case, the so-called fast deployable antenna, WOF antenna, you can just implement here and then checking the UAVs upstairs. Okay, and we want to have it with you, by you, and for everyone, of course. What I've learned so far is interdisciplinary collaboration works very well with hackers, science, and volunteers, and I'm really grateful for this. Almost everything is already available. We just have to bring it together in a sensible way. We have to keep on working because it's hard, but it's really doable. So your communities are really great because we have a lot of support for the Constellation platform from the Czech space and possibly for you. And of course, space rocks. So I'm done. So